Today on the Perception in Action podcast, can athletes perceive which balls, sticks, bats, rackets, etc. afford the greatest opportunity for hitting, throwing, etc.? What information do they use for this, and how does it relate to Gibson's concept of dynamic touch? How can we use this to better design and fit sports equipment? So it's time for a call to action. Hi, this is Rob Gray from Arizona State University. I've been on a now over 25-year journey as a researcher, professor, and high-performance consultant to understand how we acquire and adapt our perceptual motor skills. Welcome to the Perception in Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. Before we get to today's topic, I want to tell you about a couple extra things that might interest you if you're enjoying the podcast. First, my book, How We Learn to Move, A Revolution in the Way We Coach and Practice Sports Skills, is now available in audiobook format. You can find it on Audible or Amazon. Second, if you're interested in working directly with me, I currently have openings in my monthly mentorship program. This includes monthly Zoom meetings, either one-on-one or with your staff, analysis of your practice designs, and a monthly group discussion with coaches and instructors from a range of different sports. To find out more, please go to patreon.com/perceptionaction. Now on to the show. So on today's episode, I want to look at the research on the affordances of sports equipment, how athletes perceive them, and how we might use this knowledge for equipment fitting and design. Imagine you're going to start playing baseball. You walk up to a rack of baseball bats. How do you know which one you should use to achieve the best performance? What weight should it be? How thick? What length? Once you do pick a bat, where on the bat should you be attempting to hit the ball? Right at the end, closer to the handle, etc. Once you figure that out, how do you control your movement to achieve the contact with the ball at this point? All of these things are referring to affordances, opportunities for action created by different objects, in this case, bats. Same goes for golf clubs, tennis rackets, cricket bats, etc. Can we really perceive not just the physical dimensions of an object, but what it affords us? Not surprisingly, James Gibson was all over this problem. In 1966, he introduced the concept of dynamic touch. When an object like a bat or a racket is grasped and wielded, that is, it's lifted and moved around in space, this creates deformation in our body tissues. In particular, there'll be changes in the length of the tendons and muscles and ligaments in our body. Critically, and consistent with the idea of the ambient array first introduced for vision, the deformations are not random. They will depend on the physical characteristics of the object being wielded. Heavier objects will create more tension in the muscles than lighter objects, longer, different than shorter, etc. So, just as is the case with vision, objects in our environment structure the information we receive from our senses. That is, they alter it in a way that is directly related to their properties or affordances. Therefore, it is possible that we can perceive the affordances of objects directly through information provided by our sense of touch. Note, this is typically referred to as haptics, which combines passive touch with information from our kinesthetic senses created by movement. To understand this more, let's dive into some research studies on this topic. One of the first studies to look at dynamic touch in a sports context was conducted by Claudia Carello and colleagues in 1999. This study was focused on our ability to perceive the optimal contact point on a bat or racket, what we commonly refer to as the sweet spot. The sweet spot, or what is technically called the center of percussion of a bat, is the location at which contact with the ball will produce the minimal vibration in the bat. When the contact point occurs at another location, it provides high frequency, sometimes even painful vibrations that most critically result in less force being transferred to the ball and it not going as far. If you think about it, there's no visual information about the location of the sweet spot, nor could we find it by just touching the bat with our fingers. But if Gibson is right, there should be information provided by dynamic touch or haptics. That is, when we wield the bat and swing it around, the deformation in our muscles, tendons, and ligaments will depend on the mass distribution of the bat, which determines the location of the sweet spot. Therefore, there should be information available for the direct perception of the sweet spot location. Note that we should also be able to perceive this without having to hit and experience the vibrations produced by different points of contact, because there is dynamic touch information available from just wielding the bat. To investigate this, Corello and colleagues conducted 2 experiments. In the first experiment, 2 groups, a group of expert tennis players and a group of novices, were asked to make judgments about the sweet spots of standard off-the-shelf Wilson tennis rackets. In the study, participants were asked to indicate after wielding and moving the racket around for as long as they liked, quote, the place on the racket at which one would want to make contact with the ball. Note, critically, they're not asking for some abstract physical property like the length or point of least vibration. They're asking about an affordance, the place on the racket that affords the best striking of the ball. Participants indicated their choice by positioning a racket so that a tennis ball mounted on the table was at the preferred contact point. The participant could not see their hand, the racket, or the ball when performing the task. This was done for 6 different rackets with centers of percussion that ranged from 35 to 48 centimeters from the end of the racket. What was found? For both the novice and experts, the point at which they indicated they would like to make contact with the ball was highly similar, within a 1 to 2 centimeters distance to the location of the actual sweet spot for all rackets, suggesting that indeed we can perceive this location through dynamic touch. There were no significant differences at all between the novices and experts. In experiment 2, the authors replicated these findings using metal rods with adjustable weights instead of tennis rackets. The advantage of the weighted rods was that it allowed the authors to tease the different information sources apart the participants could be using. What was found here? While participants' perception of the sweet spot were influenced by the simple physical dimensions of the rod, like its length and mass, they were most strongly influenced when both mass and length were taken into account together. The authors proposed that this indicates that the information used to perceive the optimal location for striking the ball is related to what is called moments of inertia. A moment of inertia basically reflects the degree to which an object resists rotational acceleration. Think about swinging something like a sledgehammer. Because its weight is distributed mostly at the end, it has a very high moment of inertia. It's difficult to get it started moving. So key point number 1 here, that applies to today's specific topic and direct perception more broadly. The information we pick up from the environment is usually very complex, higher order information that is not easy to simply describe in words. We're not perceiving simple, general physical properties of objects like lengths and widths, but rather complex dynamics of the object like moments of inertia. Final point here. Note that in both studies there was no effect of tennis expertise. This suggests that the affordance of the optimal striking location for an implement is something that we learn through interactions with objects in our everyday life. We don't have to play tennis and get feedback about where the ball goes when contacting the different locations on the racket. Where we would expect to see this expertise difference emerge is in the control of the action. While novices may be just as good at perceiving the location of the sweet spot as experts, they likely would be far inferior at coordinating their movements to achieve contact with the ball at this location. The second body of research I want to look at is the work on affordance of throwability done by Jeff Bingham and colleagues. In a series of studies, these authors have shown that when given a set of balls of different sizes and weights, athletes experienced at long-distance throwing can select the ball that will result in the longest throw after wielding the objects in their hand. Note that in their studies, they have the participants actually throw the different objects, and indeed the one they thought they could throw the furthest is the one that actually goes the furthest. Similar to what we saw in the perception of the sweet spot, the affordance is not perceived via a simple property just like the object's size or weight, but rather a complex combination of the two. The optimal weight depends on the object's size. To quote the authors, "This is an exemplary example of an affordance property. It is physical, real, and relational. It is composed of a specific relation between the size and weight of graspable objects. It is functional. It is defined in relation to a human action, throwing, and nothing picks out the property but the relevant functional context. In particular, there is no word for this affordance property, at least not in English. Finally, this complex property is perceptible by hefting graspable objects." End quote. Interestingly, unlike the sweet spot, perceiving this affordance does seem to depend on task-specific experience. Zhu and Bingham found that unskilled throwers were unable to select optimal objects for throwing with any accuracy, but that once they had learned to throw long distance, they could also now perceive the affordance. They could now select objects they could throw to a maximum distance, even when they had no experience throwing some of those objects. What is the information that the throwers are using to perceive this affordance? Bingham and colleagues have proposed it relates to information provided by the stiffness of the tendons in the wrist. Quote, object size and weight might affect the dynamics of throwing and the dynamics of hefting in similar ways, and this similarity will allow hefting to provide information about the affordance of throwing. They suggested that the effect of object size on wrist stiffness and concurrent effects of object weight on the timing of wrist motion would be the basis of this symmetry. This hypothesized mechanism is a type of smart perceptual mechanism, as proposed by Runson. Smartness refers to particular lawful circumstances of which the perceptual system takes advantage. End quote. So essentially, they're arguing that the information we use to grasp and hold a ball, not let it fall, that is the dynamic information from the tendons in our fingers and wrist, also contributes to the control of movement of a hand and wrist when throwing, getting it at the right angle, releasing it at the right point. They suggest this is a smart mechanism, which I first discussed back in episode 362, because it's taking advantage of a simple shortcut that allows the perceiver to get the required variable they need. In 2012, Hedrick and colleagues investigated the affordances perceived for different cricket bats. In discussing previous work in the area, they emphasized the key point that although this dynamic touch information is always available, the performer needs to educate their attention to it or become attuned to it to be able to use it. Quote, in order to select a tool or implement that offers affordances for completing a specific task, participants must exhibit perceptual attunement to the physical properties of the tool that make it suitable for the task. Perceptual attunement refers to an individual's learned ability to detect key information for a given task that has the potential to influence emergent decision-making behaviors. End quote. Furthermore, a point that should be evident, but we haven't really stated yet, is the perception of these affordances is very individual. Quote, preferences for bat selection are individualized depending on the individual constraints such as playing style, whether the person's aggressive or conservative, body proportions, and muscular strength. End quote. Getting to the actual study, 11 male cricketers from an elite school cricket development program first wielded 6 cricket bats exhibiting different mass and moments of inertia characteristics while blindfolded. They are asked to identify the 3 bats they preferred the most for hitting a ball to a maximum distance by performing what is called a front foot straight drive. Next, participants actually attempted to hit balls projected from a ball machine using each of the 6 bats to enable kinematic analysis of the performance with each implement. What was found? Results for the wielding task revealed individual differences in the preferences for bat characteristics across the participants. However, typically the bats with the smallest mass and moments of inertia were most preferred, being the first choice in 65% of the cases. Moreover, the 2 bats with the greatest mass and moments of inertia were the least favored across all the choices. Finally, data from the wielding tasks suggested that the moment of inertia is what influenced choices. For example, when 2 bats had the same mass but different in moment of inertia, participants picked the one with the lower moment of inertia. Interestingly, there were not really any significant differences in the performance outcomes, that is, the speed and distance the ball went when it was hit for the different bats, even though participants had clear preferences for the bats with the smaller moments of inertia. This occurred because these skilled batters could adapt their swing effectively for the different bats. In particular, kinematic analysis revealed that they adjusted their preparatory step movements and swing duration to account for the higher moments of inertia and mass of some of the bats. This is an important point that we're going to see more of in a second. Perceiving the affordances of equipment is not merely about selecting the best bat or ball. Attunement to this information also allows a performer to adapt their movement to changes in the constraints. In Bernstein's terms, picking up dynamic touch information related to the moment of inertia allows a performer to be more adaptable and dexterous. Quote from the authors, participants were observed to display system degeneracy, whereby the perceived affordances of each bat resulted in the emergence of different kinematic patterns and strategies in order to achieve the same performance outcome. Furthermore, variations in emergent behavior during the hitting task revealed that the skilled youth participants in the study were able to adapt or recalibrate their movement patterns in response to the affordance offered by different bat characteristics, while still achieving the prescribed task objectives. End quote. Remember, moment of inertia is a dynamic property that reveals itself when you move an object. Therefore, not surprisingly, being attuned to this information actually helps control the movement of the object itself. Next, I want to look at another interesting application of dynamic touch, the perception of string tension in tennis or badminton rackets. For those that don't know, athletes in these sports generally believe that playing performance is enhanced if the quote-unquote right string tension is chosen for their rackets. Often we hear that elite tennis players prefer a particular string tension, and it has to be frequently checked and adjusted during a match. Broadly, higher string tensions allow for more transfer of force and thus higher ball velocities, but are sometimes more difficult to control, resulting in lower accuracy. Early research on this topic seemed to completely contradict this idea, as elite players were found to be insensitive to differences in string tension. In 2013, Zhu investigated this issue using an affordance-based approach. 12 adult badminton players, 4 expert, 4 recreational, and 4 novice, were first asked to determine the difference between string tensions on rackets and select the tension that would allow for the most powerful stroke. So again, focusing on the perception of the affordance. The same racket strung with 8 different tensions, ranging from 16 to 30 pounds, were used. An interesting twist in this study is that participants were allowed to use the senses other than haptics and touch. If you think about it, there is information about a racket's string tension available from vision, watching the strings deform when they make contact, and audition, the sound the racket makes at contact. In the study, participants made separate judgments just using each one of these modalities. In the visual mode, participants watched 8 silent video clips of a ball bounced on the respective strings. In the auditory mode, participants heard 8 soundtracks of the string beds being hit by the experimenter's hand. And finally, in the haptic mode, participants pressed the string bed of each racket using their fingers with their eyes closed and ears plugged. Following these judgments, there was a performance task in which participants were asked to strike a shuttlecock suspended from above their head with as much force as possible. What was found? If we look at the performance first, interestingly, the mean maximum speeds varied with the string tension, but in different ways for different skill levels. As the string tension was increased, the speed of the stroke decreased for novice players, increased for recreational players, and remained the same for experts, indicating that the effect of string tension on power strokes depends on the player's level of expertise. Similar to what we just saw in the cricket study, the skilled badminton players are showing evidence of dexterity, the ability to produce the same high-velocity stroke under changing constraints. Turning to the affordance judgments, players at all levels had a clearer preference for certain tensions, with experts and recreational players selecting higher tensions than novices. These judgments were not significantly different for the different sensory modalities. Interestingly, it was only for the recreational players that the preferred string tension was the one that actually resulted in the highest maximal velocity of the shot. This was not the case for novices or experts. Let's look at why. For novices, this lack of calibration makes sense. As we saw in the Bingham throwing studies, perceiving the equipment that is optimal for performance requires experience performing the action. We need to become attuned to the information specifying the affordance. Novices tended to select a string tension that was too high for their movement pattern. Quote, in producing a power stroke, novice players merely used elbow flexion and extension with little follow-through after striking. Skilled players performed strokes quite differently than less skilled players. Both recreational and expert players used a full body motion, starting with a side stance, then swinging the racket in a series of movements at major joints, starting with the ankle and knee, and proceeding up to the wrist and finger joints to the racket. End quote. So in other words, the novices were freezing degrees of freedom in the stroke, which necessitates using a lower string tension to keep control of the shot. But what about the experts? The reason their preference for string tension didn't align with their performance is because of their adaptability. They produced the same velocity outcome for all the different string tensions. So why then do they seem to show a preference for a particular string tension? The authors propose an interesting explanation. Quote, presumably, expert players were able to use wrist and finger flexion to increase speed at the racket head, even more to compensate for the loss of energy when using lower string tensions. However, this method for generating additional speed comes with a cost. It takes more energy and may cause fatigue. For this reason, high string tensions are preferred by experts." End quote. So in other words, even though they can produce the same outcome for the different rackets, they're perceiving a more complex affordance, efficiency, that takes both outcome and effort into account. As a Canadian, I would be remiss if I didn't talk about some of the work that has been done on hockey in this area. In particular, the study by Hove, Riley, and Shockley in 2006. In this study, the authors investigated perceiver sensitivity to the affordances of hockey sticks for either power, transferring maximal force to a puck, or precision, controlling the puck to move around a small object, tasks. The moments of inertia of hockey sticks were manipulated by placing weights on the sticks in one of three different positions: the top of the stick near the handle, the middle, or the bottom near the blade. It was hypothesized that participants would choose the bottom-weighted stick for the power task and the top-weighted stick for the precision task. This was investigated across 4 experiments. In experiment 1, 12 novices were asked to rate the different sticks for the 2 tasks. Note, the positions of the weights were masked visually by placing foam coverings at each of the locations. The predicted relationship was found. Participants preferred the stick with the mass concentrated furthest away from the point of the grasp when determining the stick's usefulness for exerting force. In contrast, participants preferred the stick with a mass distribution concentrated nearest the point of grasp when rating the stick's usefulness for a precision control task. So again, similar to the Carrillo sweet spot study, wielding objects in everyday life, presumably things like hammers, seems to make us attuned to this affordance. Specific hockey experience was not required. In experiment 2, participants made the same judgments, but also actually performed the 2 hockey tasks. Importantly, they were asked to rate the sticks both before and after the power and precision tasks were completed. What was found? For the precision task, the stick ratings were the same both before and after performance of the action. They preferred the top-weighted stick. But this was not the case for the power task. Before performing the task, the bottom-weighted stick was given the highest rating, while after performing, the sticks were all given the same rating. What's going on here? The authors proposed that through performing the task, these novice participants learned that because a hockey puck is relatively small, even a task focusing on power requires some precision to effectively make contact with the puck. This idea was supported by the results of a third experiment in which the puck was replaced with a large inflatable ball, thus removing some of the precision constraints. In this case, the stick ratings were the same both before and after performing the action. Finally, in experiment 4, the authors recruited expert hockey players from the varsity team at Miami University and performed the exact same study. What was found? Remember, novices tend to choose the bottom-weighted stick for power and the top-weighted stick for precision, with this judgment changing after experience performing the task. Does this also occur for experts? No. Right from the start, experts had a clear preference for top-weighted sticks for both the power and precision task. This was likely due to 2 reasons. First, through their playing experience, they learned that even a powerful action like a slap shot in hockey requires a fair degree of precision. Second, similar to what we just saw in the badminton study, it's likely their coordination pattern had many more degrees of freedom involved, allowing force to be generated more effectively, removing the necessity of a counterweight on the stick to do the work for them. So what does all this mean for the design and fitting of sports equipment like baseball bats and golf clubs? Well, first, obviously one size does not fit all. The actions afforded by equipment of different shapes, sizes, and weight distributions will depend on the individual constraints of the user. Second, the athletes themselves, through the perception of affordances provided by dynamic touch information, are the ones most attuned to what equipment will be best for them. Third, we need to move beyond looking at the simple static properties of equipment, like club length, club head size, loft, etc., towards the properties that actually influence the task dynamic, like moment of inertia. Finally, maybe it's not really that important what equipment an athlete chooses, because if we train to be dexterous and adaptable, differences in equipment dimensions is something that seems to be easily adapted to. However, as we saw in the badminton study, perhaps there are still gains that could be made in terms of things like efficiency and injury prevention. These topics were discussed nicely in a recent paper on golf by Paul Glazier, link in the show notes. He notes that there have been some, but still limited efforts towards a more ecological approach in golf club design and fitting. For For example, an important thing to emphasize is that due to the dexterity of skilled performers we have seen in some of the studies today, we can't simply predict the effects of equipment changes using simple biomechanical models and simple measurements. We need to consider how these changes in the constraints influence the coordination pattern for individual golfers. Consider the study by Warabetz and Stefan, in which the influence of shaft stiffness on clubhead speed in a group of 40 golfers was examined. It was found that, on average, there was no significant difference in clubhead speed between drivers with shafts of different stiffness. However, when data from individual golfers were analyzed, significant differences in clubhead speed were found for 27 golfers. 17 golfers produced their highest clubhead speed with one of the two drivers with the most flexible shafts, whereas only 4 golfers produced the highest clubhead speed with one of the two drivers with the stiffest shaft. As Paul notes, quote, "The results of these type of studies indicate that the properties of golf clubs can have a large impact on performance, but are dependent on how a golfer loads the club, which are, in turn, dictated in a large part by the golfer's individual constraints, specifically the force length and force velocity relationships of skeletal muscles." End quote. Paul also discusses attempts to incorporate more dynamical properties in the fitting process for golf clubs, including a variable called swing weight and attempts to use moment of inertia. Quote, "Golf clubs could be fitted according to the affordances they offer the golfer using them. That is, woods and long irons could be fitted with inertial characteristics that the golfer deems to afford power hitting, whereas short irons and wedges could be fitted with inertial characteristics that the golfer deems to afford precision hitting." End quote. So, to sum up, here are a few key points from what we've seen in today's episode. 1. Dynamic touch allows users of implements to perceive the utility of a given implement for a given task. In other words, to perceive an implement's affordances. 2. These affordances are learned through experience interacting with equipment, with some learned through everyday experience and some requiring more sport-specific experience. 3. Consistent with Brett Fagen's concept of affordance-based control, perceiving affordances are not merely for action selection, in this case equipment selection. Attunement to this information that allows you to perceive the affordance is also critical for the online control of the action. As we saw in several examples today, the information offered through dynamic touch allows skilled performers to achieve repetition without repetition. That is, achieve the same outcome, for example, a high-velocity shot, regardless of bat mass or string tension. 4. The specifying information used to perceive the affordances we're talking about today, and most affordances for that matter, is usually very complex and often multisensory. It can't be expressed simply in words with simple phrases. This is something I'm going to dive into in the future. A common question I get from a lot of people is, how do I know what the specifying information is for my task? And I'm going to dive into that in a bit more. Finally, number 5, I think again this points to using equipment as a diagnostic constraint manipulation. That is, giving people different types of equipment and seeing how they adapt. Okay, that's it for today's episode. Remember, you can contact me at robgray@asu.edu or follow me on Twitter at ShakyWeights. To find out more about the podcast, please check out perceptionaction.com. Finally, to support the podcast and receive bonus materials, including written transcripts, please head over to patreon.com/perceptionaction. This is Rob Gray from ASU. Cheers for now, and keep them coupled.